Cygnus Eye lecture, where it's a real pleasure for us to have with us a very distinguished astronomer, Dr. Gabor Basri from University of California, Berkeley. Dr. Basri is a native of Colorado, and grew up in the Fort Collins area. Has a bachelor's degree in physics from Stanford and a PhD in astrophysics from the University of Colorado. He's been has a long list of distinguished awards, which I won't take time to read, but he's been at the UC Berkeley since leaving CU and is on the faculty there in the Department of Astronomy. He's going to talk to us tonight on the birth of stars and planets. So, Basri?
Thank you very much, Dean. Thanks for inviting me here. I love talking about this topic because it's one of very general interest. So, people have been wondering about how the Earth got here and how the Sun got here since people have been wondering. And of course, you've heard lots of myths from various cultures about the formation of the Earth and the formation of the Sun and so on. And so, I'm going to give you the latest myth. Except this myth is unlike the other myths in that I'm going to back this one up with lots of pictures of these things actually going on. So I think for the first time in human history, we have the ability to actually see how solar systems are made. And this has really only happened in the past 20 years or so. So it's been an exciting time in astronomy. It's not over yet. There's a fair amount of advances that are going to occur in the next 20 years that will tell us even more about how solar systems are formed. But I think that it's an appropriate time to talk about this now. And it also generates a lot of pretty pictures. So I hope that I know there are a variety of people here. I will try not to go over anyone's head, but I will promise you that at least you'll see some pretty pictures. And I actually do encourage people to raise their hand during the lecture if I'm confusing you or you have a question about something. Go ahead and stop me. I can always adjust the lecture to accommodate such things. So please do. I prefer interactive audiences. So with that, go ahead and kill some of the lights. I guess there's still some lights left. Now, if everyone's okay with this, we'll go with this. So maybe we should focus it. Let's see. That's probably. Each one is different. Maybe we turn the lens. Yeah, there we go. You can tell that I'm an observer, so I can figure that out, as opposed to a theorist. Okay. So probably most of you know the basic story behind star formation. This is a picture taken of the Milky Way, our galaxy. It's a pretty close-up picture. You see lots and lots of stars. But you also see that apparently there's a region here where stars are missing. And in the last century, when people saw this, they actually thought stars were missing there. That this was some kind of hole in the galaxy. But today we know that this is actually a dark cloud, which is blocking the view of all the stars behind it. So the few stars that you see there, you can now interpret as being in front of this dark cloud. And all the stuff that would look like this if it weren't for this dark cloud there. The dark cloud is made of what we call dust. Astronomers call it dust. Original name. It's not like the dust under your bed, exactly. It's much smaller. These are micron-sized particles of silicates and graphites. They are produced in the atmospheres of red giant stars. As stars are dying, they get very cool. Carbon and silicon condense out as the star is sort of blowing its atmosphere away. So this stuff condenses out and is blown out into the interstellar medium, and later it collects into clouds again, and this is one such cloud. Along with that dust is about 100 times its mass in gas. And when we say gas in astronomy, we mean mostly hydrogen, 90% hydrogen and 10% helium by number, which is what the universe is made of, basically. So this is it's a cloud which is not quite primordial stuff. It's mostly hydrogen and helium, but it has this dust in it. So these kinds of clouds didn't occur early in the galaxy before the stars had made the dust. But these days, there's plenty of this dust around. And the dust is just a marker here. It's a marker for a place in the medium between the stars, the interstellar medium, where for one reason or another, and we don't understand this fully, the stuff has become more dense. There's been a collection into a cloud, and around this cloud is a very diffuse interstellar medium with not so much dust in it that's kind of holding it in place. That's the site of star formation. And one thing that we certainly know is that star formation is an ongoing process in our galaxy. It's not as though the galaxy was made a long time ago and all the stars are in it. It's still full of gas and dust, and it's still producing stars at a rate of about 2 to 10 per year, 2 to 10 solar masses per year. Somewhere in the galaxy, a star is formed. As you'll hear later, it's not like one day it's not there and the next day it's there. It takes, on average, a few 100,000 years to actually collapse one of these clouds into stars, but it's an ongoing process, and that's sort of the average formation rate. So here is another view of an interstellar region where stars are made. This is the famous Horsehead Nebula. Maybe I should do it this way. So it looks like a horse head. That is just a cloud of dust, again. The dust is dark, it blocks the light behind it, so you can see that this cloud here is in front of this red glowing cloud behind it. But all of this stuff is the stuff of which stars should be and are in fact being made. So this is actually a region of ongoing star formation right now. It's this condensed cloud. This very bright star here was made in that cloud only a couple of million years ago. And you have to get used to the way astronomers talk about this stuff. When I say a very short time, I mean a million years or less. And if I say a long time, I mean maybe a billion years. So those are the time scales, but you can see that there's sort of inhomogeneous, there are clumps, some of them are being lit up by stars that were formed there, so these blue areas are just reflecting starlight, much the way our sky is blue. They reflect blue light preferentially. The red is the hydrogen itself glowing, fluorescing under the ultraviolet radiation from this star. So when you look at pictures of nebulae, you are seeing gas and dust, which is only seen because stars are forming there and lighting it up. So what I want to talk about today is the actual process by which stars are made, first of all, and then I will go on and talk about, once you make stars, what about making planets, too. Let's try the first slide now.
Just click it from here.
Oh, okay. Great. When these clouds form in the interstellar medium, most of them are not all that dense. And they're not dense enough, in fact, to collapse under their own weight and make stars. But some fraction of them become quite dense. And they become what we call molecular clouds. And the reason we call them that is because the hydrogen, you saw the glowing red hydrogen in the last slide, that hydrogen gets dense enough that the hydrogen atoms combine into molecules, and it becomes molecular hydrogen. And then you can't see it so easily, and so we have to use proxy tracers. This one was done in carbon monoxide. This is actually an image taken by a radio telescope of a molecular cloud, and the emission that you see is all coming from carbon monoxide. But we know the ratio of carbon monoxide to molecular hydrogen, so we can tell how much mass is in this cloud. Just to give you a scale here, this would be maybe 50 light years along this whole cloud. and the amount of mass that's in there might be 100,000 solar masses, 100,000 times the mass of our sun. So this is a dense enough cloud that in the insides of it, that dust blocks all starlight. So inside the cloud, it gets very cold and dense, and it's kind of protected from the ultraviolet radiation of our galaxy. And molecules can form and stay. And that's what you're seeing here, the molecular emission. So the molecular radio emission is a tracer of where the interstellar medium has gotten quite dense enough to make these molecular clouds. And it's only there that the cloud finally becomes so dense it can collapse under its own weight and make a star. This is a optical picture of the same kind of region. So now you're not seeing the insides of it. The radio telescope is able to penetrate all the way through the cloud. You can see molecular emission from the whole thing. Optically, as you saw, dust kind of blocks your view. So here you're sort of more just seeing the surface of it. But this is several light years across, and you're just seeing the glowing outside of what is in fact a big complex of molecular material, which will make stars. This is a rather wide field picture. The constellation of Orion, for those of you who know it, sort of encompasses this area here. This is the Milky Way in the region of Orion. And this picture is taken in infrared light. Infrared, of course, is sort of heat radiation. What happens is the dust, as stars begin to form in there, the dust heats up and begins to emit infrared light. And infrared light penetrates the dust better than visible light does. So we can actually see down into these clouds in the infrared light, where we can only see the tops of them, basically, with visible wavelengths. So you're seeing an infrared picture, and all this glowing stuff is picking out hot dust. And the dust is glowing because stars are forming in there. So all these bright regions here, we know, are regions where stars are just now forming or have recently formed and heating the dust up. Notice this ring-like feature here, too. Hello. That's this again. We've zoomed in a little bit. In the middle there is a pretty bright star that formed recently. And as we'll hear, once you make a luminous star, it starts damaging its environment. It starts actually powering a high-velocity wind, and its radiation moves out and ionizes things and sort of starts perturbing the interstellar medium, and essentially it's blowing a bubble in the dust. And that will eventually disrupt that whole part of the cloud complex. And so the process of star formation also is a process of destruction. The stars, in the end, destroy their own nursery. And so it turns out that when you have a molecular cloud with 100,000 solar masses, it doesn't make 100,000 suns. The process is a good deal less efficient than that. You might make 10,000 or 1,000 stars before the cloud is disrupted. That whole process goes on over a sort of 10 million years or so, and by then the star formation region has been shredded and no more stars form there, and that stuff goes out and eventually clumps into clouds somewhere else and can start again. This graph is a little more technical. Don't worry about it. I'm just going to use it to remind myself of a few things I want to tell you. So this is sort of a cutaway through a molecular cloud. Here's the molecular cloud here. The scale, as I said, is tens of light years. These are huge features in the galaxy. And all I wanted to say about it really, first of all, on the outside, the densities are very low. Sort of 100th of a particle per cubic centimeter. Or you have to have a block 100 cubic centimeters in order to find one atom in it. That's what the medium between the stars is really like, except for where these clouds are. As you come to the cloud, there's kind of a skin of atomic hydrogen on it, where this very low density stuff is very hot, so the hydrogen is ionized. The electrons are stripped off. It's not even neutral hydrogen. there's a skin on the cloud where the hydrogen is neutral, and the temperature is something like 10,000 degrees. So you can think of there's sort of a hot skin to the cloud with atomic hydrogen in it. And then inside of that, the density is much more, like 300 particles per cubic centimeter. So that's the sense in which these are clouds inside an empty sky. And the temperature is also very low, 10 degrees above absolute zero. So these are very cold, relatively dense concentrations of hydrogen molecules. Within those, there are even denser concentrations, and that's where you make stars. So this is all, it's kind of a turbulent cloud. You can think of the gases flowing here and there and running into itself, and it makes clumps that are much denser yet. This has the density of something like 10,000 particles per cubic centimeter, and that's just sort of the average density across it. And the size of it might be maybe only one light year. Okay, and the mass in one of those clumps might only be 1 or 2 times the mass of our sun. So that shows you sort of, it's these little clumps within the molecular cloud which actually collapse to make stars. The cloud as a whole is just there to produce these clumps. And once you make one of these very dense clumps, then it will actually collapse to make a star. Well, that was sort of a theoretical picture. Here's a real picture. Most of you have seen this. This is one of the most famous images from the Hubble Space Telescope. This is a molecular cloud. You can see the dark dust. It's obvious. This is. It looks like a pillar of dust. Of course, there's no down or up in this picture. It's just, I can show it this way just as well. It's just a cloud, and this one is kind of long. And in fact, that's typically how they are. They're not round clouds. They are usually stringy concentrations of gas. And what's happening here is this was a bigger cloud, and a very massive star formed. It's not in the picture. It's sort of up there, and it's now shining down on this cloud and blasting it with a high velocity wind, and it's eroding away the molecular material. And so what you see at this point in time is you actually can see it. See all this sort of blue stuff? It looks like it's kind of boiling off of the surface. The high mass star that's formed there is in fact boiling away the molecular cloud. It's got enough energy to do that. All these little finger-like things, and I have a close-up of those. So here's the top of that cloud. This gives you a better feel for the fact that the clouds are not uniform. They're very clumpy. They have, dense regions and less dense regions, and they look kind of turbulent. That's how they are. Each of these little fingers here are essentially dense clumps like the ones I was talking about. So as I said, the scale is very big. The 1 light year, is sort of the size of one of these fingers. And what's happening is there's a dense clump there. The high mass star is shining down on it, but that dense clump is casting a shadow. So the material behind it is kind of protected from the blast from the high mass star, and so it remains after the other stuff gets eroded away. So these fingers are basically shadows of dense clumps, and around them the high mass star is eroding it away, but the dense clump itself is casting a shadow which allows the material to remain longer. So that produces these long fingers. So if you ever wondered what you were actually looking at in this picture, that's what you're looking at. So we would expect that you might have a star forming sort of at the tip of each of these things. And indeed, when you look in the infrared, you often find a star buried inside there. You can't see it in optical light because the dust blocks your view. But as you use more penetrating infrared radiation, you can see in there, and you can actually see that stars are forming in those various clumps. You can also see that this isn't going to go on forever. This star is just eroding away the whole complex, and so in a few million years this will all be gone. Those stars that are forming there will be exposed, and that will be the end of the story in that region. So let's zoom in on one of those clumps now and ask what happens inside there. How does the actual process of star formation take place? Again, this is more complicated than it needs to be, so I'm just going to use it as a guide. So here's one of those clumps. The magnetic field that's in there is important. I'm not going to talk about it. So the green lines help support the cloud against collapse, for those of you who care. We won't talk about that. All we will say is that the more dense the material is, the more likely it is to collapse. And the way these things are structured, they are densest in the middle. And so the middle, the very center of the core, is most dense and most likely to collapse first. And so in fact, the way the star is formed is by an inside-out collapse. The collapse begins at the center because that's the densest, and stuff starts falling in. It's no longer supported by magnetic fields or by thermal pressure, and it falls towards the center, where of course it finally hits, and everything comes to the center and hits itself, hits the stuff coming the other way, and you begin to build up a star there. Okay. Well, as stuff falls in, the free fall velocity, it's just dropping, right? And there's no air resistance, if you like. So it falls in at increasingly high velocities. In fact, supersonically. So stuff's falling faster than the speed of sound in this medium, which means that the information that it fell can only propagate out at the speed of sound. So basically stuff drops away and gets to the center quickly, and the information that it fell, slowly eats its way out into the cloud. So you develop an empty center with an object, the star, at the center. And then there's kind of an empty space. The rest of the cloud doesn't know what happened yet. And then the information that it's falling moves out at the speed of sound. It's sort of an implosion wave. It eats its way out through the core. And the thing, as the wave reaches any given point, it starts falling towards the center. So you can think of it as an inside-out collapse, starting in the center first. Of course, when the stuff lands there, it's moving very fast. It strikes the object at the center, and a lot of heat is released. So that object is glowing. In fact, it heats up to several thousand degrees, like a star. Although there's no nuclear fusion or anything going on yet. So the initial energy for all this just comes from gravity, potential energy of gravity. Stuff drops in, heats it up, lights up like a star. So this is glowing like a star, but of course it's surrounded by this dense core, which has dust and everything. So the light can't get out, actually. The light shines back out through this empty region and illuminates the implosion wave area. And there it's absorbed by the dust and converted back to heat. Yeah. Oh, that's a few kilometers per second. And the free fall velocities are a few hundred kilometers per second. So it's much faster. And so because it's a few kilometers per second and the scale of this is sort of a light year, you can work it out. It takes a few 100,000 years for this thing to collapse. So that sets the basic time scale for star formation. It's just that exactly. The light comes back out, it's absorbed by this dust, converted to heat, heats infrared radiation. Infrared radiation can eventually escape this. So from the outside, what you first see is a very huge glowing core, which is glowing in the infrared. You don't actually see the star forming at the center. If you're looking in visible or infrared light, you see this. You see the outer surface of the dust, which is letting the light go, and that's what you see. So you see a very big glowing infrared object, and we have to infer what's going on inside of that. But that's the first sign of a forming star. Yeah. Oh, the galaxy is pervaded by a magnetic field. Its cause is pretty complex, but basically there's a lot of charged particles in the galaxy and they move around. It makes a dynamo and generates field. It's not very strong. The field, these green lines here, are of order 30 microgauss. That's a typical field in the galaxy. But charged particles also can't cross field lines. So as the thing wants to collapse, it's got to either drag the field in with it, or it has to let the field slip through it. And that kind of slows things down. And it's also, before it's dense enough, that actually prevents it from collapsing. So it has to become dense enough that the pull of gravity by the matter is able to overcome the resistance of the magnetic field being dragged in. But yeah. Okay, well, I said everything's dropping down on the star. I lied. That's not quite right. And in fact, the fact that it's not quite right is responsible for planets. So it's an important detail not to gloss over. So let me back up a little bit and talk about angular momentum for a second. There are various levels of sophistication here. I'll be insulting some people. Other people will be interested in this. There is a quantity called angular momentum, which is basically the spin inertia of something. It's a mass times the velocity of which it's moving times the radius from the rotation axis that you are. Okay, so you've all seen this in action when a skater is spinning. If she puts her arms out, her arms are out at a certain distance from the rotation axis, and they're moving at a certain speed. Okay? As she pulls her arms in, the product of the velocity and the distance has to remain constant. Angular momentum is conserved. So since the distance is decreasing, the velocity has to increase to compensate. That is why when skaters pull their arms in, they begin to spin faster and faster. So you've seen that in action. Okay, that same principle is going to operate here as well. So if I had a ball like this, and it's spinning with a certain velocity at the surface, and I contract the ball, then conservation of the angular momentum tells me that the velocity has to increase as the radius decreases. Okay? That's the principle. Now these molecular cloud cores that I was talking about, they all have some spin. It ain't much. They spin once every few million years. Okay? On the other hand, they're a light year across. Now, a star is not a light year across, right? A star is a few light seconds across, or a light second across. A second and a year have a big ratio with each other, like 10 million. So, if the velocity was very slow to begin with, but I decreased the radius by 10 million times, you can imagine the velocity is going to be a whole lot more. And in fact, what happens is before you could make a star, you run into a problem. Because the other thing that happens when you're spinning, if you spin a rock on a string, right? You spin it around, you feel a force pulling out. It's called centrifugal force. Okay? That force pulls out away from the center of rotation. Well, what's acting like a string in this situation? Well, it's gravity. Gravity is the only thing pulling things towards the center. And as I spin them faster and faster, this force that pulls them away from the center grows. Until finally it grows to the point where it can counteract gravity. And when I get to that point, I'm not going to fall in anymore. I'm going to have to stop there. I'm going to have to stay at that orbit in which centrifugal force balances gravity. In fact, that's how orbits are determined. So they are the path at which centrifugal force just counteracts gravity. That's why the space shuttle doesn't fall down, because its centrifugal force out counteracts the Earth's gravity in. That's one way to look at it. Physicists here might be quivering, but we'll leave it at that. Okay. So, we have this collapsing core, and it has a little bit of spin. Now, gravity is pulling towards the center. Okay? But there's some rotation axis for this core as well. As material is pulled towards the rotation axis, it gets more centrifugal force. So it becomes harder and harder for gravity to pull it in. On the other hand, if I drop the material down from here down to the equatorial plane, I don't change the distance to the rotation axis. So that's easy to do. So it's fine for gravity to pull stuff down this way. And of course, this is also down in this picture because gravity is at the center here. So I can go this way and I can go that way without running into any angular momentum problems. But when I try to go this way towards the center, I have this increasing centrifugal force. So it's easy for gravity to collapse the thing towards the equatorial plane, but it's hard for it to pull it in towards the rotation axis. What does this mean? Why do I care about all this? Well, this is what's going to happen. The stuff that is near the rotation axis has low angular momentum because it had low R to begin with. So it just drops right down to the center. So the initial stuff that forms a star just sort of falls in along the rotation axis. But the stuff that's coming from the outer parts, as it falls in, it starts spinning faster and faster until gravity is counteracted by centrifugal force. It can come down, though, to the equatorial plane, where it is met by other stuff that's coming up from the other side. They crash into each other, they cancel their velocity up and down, and they're just left with motion in the equatorial plane. So everything is going to settle down into this equatorial plane, and it's going to come in towards the center until centrifugal force balances it. So what's it going to end up looking like? Everything collapsed to the equatorial plane, it shrank in to some distance, not all the way to the star, and there it is, spinning. And that configuration looks like a disk. Right? So the cloud doesn't collapse to a sphere in the center, rather it collapses to a disk. And the size of the disk, the outermost radius of the disk, is just set by however much spin I had sort of on the outside of the cloud. How much can I bring that in before its centrifugal force is counteracted by the gravity of everything inside? Well, the scale of disks that are set that way is 100 to a few hundred times the distance of the Earth from the Sun. And those of you who know the size of our solar system, it's sort of 50 or 100 of these units. And that's not an accident. So the typical spin in molecular cloud cores will produce a typical disk, which is basically solar system sized. Interesting. Yeah?
This spinning, is there a law that says it has to spin, or is just some things spin and others don't?
Everything spins. It's
a law that says that has to.
Yeah, there's not a law, but what happens in practice is everything is turbulent. And in particular, in the galaxy, there's a particular effect going on, which is like in the solar system. Actually, it's not like that's pretending it is. In the solar system, the further you go from the sun, the slower you have to go around, right? It's the same. As you get away from the sun, the gravity's less, so the centrifugal force to balance it is less, so I don't have to go as fast. Okay? Now, just imagine two adjacent orbits. Okay? The inner one goes a little faster than the outer one, right? For that reason. Well, now imagine that it's not orbits, but just sort of gas there. So the inner part of the gas is going to move a little faster than the outer part of the gas. Well, that's going to kind of rub in between, right? And generate a little vortex there. Where fluid is moving at different speeds, you'll generate vorticity, spin. So that's going on in the galaxy. So automatically you're going to get some spin for that reason. Then, of course, it's much more chaotic. So as turbulent eddies pass near each other and collide off-center, they'll generate some spin and so on. So the bottom line is there's almost nothing in astronomy that doesn't have some angular momentum to it. Okay? So, but there's a typical amount of angular momentum. And as I said, that typical amount of angular momentum, given the collapse scale and the original rotation, generates a disk which is a typical solar system size. Okay, and that's why, in fact, it does that. So I expect disks. I expect a central star, and I expect a disk around it. And the disk, in order for the disk to get its material to the star, it has to somehow dump the angular momentum that it has. And one way it can do that is by generating spiral arms. You may have wondered why galaxies form spiral arms. The reason is galaxies like that are also disks. In fact, the process is basically similar, but on a galactic scale instead of a solar system scale. They collapse to a disk for the same reasons. And then gravity would still like to win. Angular momentum's in its way. So it tries to come up with a way to dump angular momentum. And it turns out that spiral arms take angular momentum from the inside and move it to the outside. And essentially toss off, stuff out here, which carries away angular momentum. And since this stuff now has less, it can move in closer. So it's a way for a disk to accrete to the center by forming spiral arms. We think something similar to this happens in solar system disks as well. They probably have spiral arms, and they have ways of dumping angular momentum from the inside to the outside so that more material can flow to the central star. So this is a picture of a galaxy, but probably a planetary disk looks something like that as well. Okay, I'm going to go back to the slides now to show you real disks. What we're going to do is, we were in Orion here. We're going to stay in the constellation of Orion, and we're going to go to the famous Orion Nebula, which is, in fact, one of the most prolific nearby star-forming regions. That's why it's a nebula. This is kind of what it looks like in a big telescope from the ground. This is probably one of the best Earth-based images of the Orion Nebula. Just to orient you, what you're looking at here is you have a molecular cloud. It's long, as usual, but it's pointed right at us, basically. So you can think of it as a big cigar. And the near end, we can't see through it, of course. We can only see the front tip. And the front tip somebody's lit it. It's been lit by the process of star formation right near the tip. Star formation is also going on inside, but we can't see that because it's hidden by the dust. But we can see it at the tip near us. So this is the tip of the cigar here. It's lit up by these 4 stars here. There are 4 of them right there, called the trapezium. Those are high-mass stars that formed in the last million years or so. They're providing all the light, basically, for this. And now we're going to zoom in on this scene and see star formation in action. So now we're closer. Here you can see the 4 stars again. It's mostly this one that provides the light. That one is several tens of times the mass of our sun. And the way stars work, that means it's 100,000 times brighter than our sun, and pretty ultraviolet too. So it's producing a tremendous amount of high energy radiation, which is lighting all this up. Okay, this is a Hubble Space Telescope image, and now we're going to basically keep zooming in on this. We're going to, in particular, look at some of these other little objects that you see here. They're all newly forming stars. So here we've gotten a little closer. Now you can see them a little better. This one looks kind of funny, doesn't it? Looks like it might have a little tail or something. Or even closer. Here's the 4 stars again. Now you can really see. There are other objects around here, and they all have little tails. And the little tails all point away from that star. So now the star is up off, you can just barely see the spikes there. Here are some more details. So they have glowing tips and little tails. Basically what's happening is the high energy particles and radiation from this big star coming down, encountering a newly forming star. There's a shock wave out front that heats up, so that's the glowing tip there. And the stuff drives by that and starts stripping away material from that little core that was trying to make a star. And that material is the tail there. So they all look a little like tadpoles. And the effect of the high mass star is that it's really kind of eating away at these poor stars that are trying to form there. Here's an even closer view of one of those. There's the glowing tip, here's the tail. And now, if you look very carefully, you see a black something inside there. That is the actual disk that I was talking about before. The cloud is mostly collapsed down to a disk. The size of the disk is therefore the size of the solar system. So that's a solar system. The diameter of that disk is probably 3 or 4 times the orbit of Pluto. So that kind of gives you a scale on this. Here is another disk right there. That disk doesn't have the shock and the tail because it's actually out in front of the situation, enough that the high-mass star hasn't gotten to it yet. We're just seeing it silhouetted against this glowing gas behind. And there again, you can see that it's a round disk, and you can actually even see the star forming in the middle of it, a little glowing red dot there. So these are the first actual pictures of newly forming stars with disks around them. And of course, most of you know, our solar system must have formed in this way because it's configured like a disk. So here they are. There's an even closer view of that. So that disk is sort of edge on, looking at it from the edge. This disk is kind of face on, and there's the star forming in the middle of it. Here's another one. You can't see it so well, but there's something dark in there too. Basically, all of these stars form with little disks. The reason they glow like this is just because of their proximity to the big bully. If they weren't near there, they wouldn't look like that. They would just be disks, but then they'd be a lot harder to see. We wouldn't have this glowing background to see them against either. So here's away from a massive star now. This is a dark cloud again. And inside of that cloud, there's a star forming. And we can see it in the infrared, but we can't see it in an optical picture like this. It's buried right about in here somewhere. But look at this. There's something else weird going on. There's something comes poking up out of the dark cloud and heads off into space, and it kind of looks like a shock wave again. And actually, back here, there's the reverse shock wave. We can actually measure the velocities of this. This is coming out at a couple hundred kilometers per second in that direction, and this one is going the other way. So something else is going on here. Here's a close-up of the one that comes punching out of the cloud. It's a stream of gas moving at several hundred kilometers per second, and it's wandering off into space like this. And as I said, there's a reverse one in the other direction. And they both point back to the star that's forming inside that cloud there. Here's a better example. This one is not sort of hidden by the dark cloud. You can't see the star itself, though. It is hidden still by its dust envelope. But pretty soon we see this jet of material. It looks pretty straight. It has shock waves periodically because it's kind of inconsistent. It blows hard and then blows soft and blows hard again, and that produces a series of shocks out the jet. And in this case too, there's a reverse jet going the other way. And here's the last, what was the first burst way out here. Sometimes you don't see it there, but it's still there. You only see it when it lights up because of shock waves, basically. So we know there's material flowing here. That is the other solution to the angular momentum problem. The disk was the first solution. Stuff came in, couldn't dump any more angular momentum, so it made a disk around the star. Then the disk tries to dump angular momentum and get stuff near the star. But when we look at these stars, they're not rotating very fast. And as I said, there's been a huge scale change. So somehow you've got to dump more angular momentum before you can actually get material onto the star and build it. And the other dump occurs right next to the star. It again involves magnetic fields, and I can't describe it here. But let's just say that their nature has a mechanism to allow the rest of the angular momentum to be thrown off at the last second along the rotation axis in both directions. and generate these very spectacular flows away from the star. They go very quickly, they have high velocity, and they carry away a lot of angular momentum. That allows the other material to then finally go onto the star and finish making it. So if we could have a picture where we can really see the star, and we can't do that yet, but maybe we'll be able to do it in 20 or 30 years, we might see this. So this would be the very inner region of the disk. There are magnetic field lines now coming out from the star itself. They interrupt the disk in the last bit, and there's a mechanism by which the field winds stuff around, and it goes shooting out in a helix along the two rotation axes, carrying away a lot of angular momentum. And that finally allows the rest of the stuff to fall onto the star. So we see those jets, and we don't see, we can't see this kind of detail, so that all comes from theory. So this is the next phase of star formation. The cloud core is still flowing in onto the disk. The region of the core near the poles, the rotation poles, has been cleared out because that was all low angular momentum stuff. So that's already fallen down. So it opens up a cavity along the rotation axis. And then there is this spectacular jet which punches away right along the axis there, carrying off the rest of the angular momentum that we need in order to make a real star. And as a natural consequence of this whole process, you get a circumstellar disk around the star of about solar system size. What the suggestion from all of that is planetary systems are probably pretty common because this is the setup to make planets. And it looks like you kind of have to get that in order to make stars. So it's not very unusual to have this situation arise. One last